So having been able to look at graphing functions, developing tables, most importantly, with your calculator, and then plotting those points carefully on the XY plane and getting a good, decent, accurate graph from which you can extrapolate answers, we now want to take those graphs and move them through what we call transformations. Now, transformation is nothing but a change, okay? Just think of that word, operation transformation, for example, that famous program on RTE, simply means watching how people change over time. So when we talk about transformations of functions, what we're simply doing is we're taking a function and we are changing it in some way, shape or form in order to become another function or to have a different appearance. Okay, now I'm going to look at linears and quadratics today, just those two, and then I'm going to pause and give you some questions to do, because I think we're going to have to creep through this in terms of the amount of volume that's in the questions themselves and in the book. And then I'm going to take a look in a separate class at how to take a full quadratic, ax squared plus bx plus c, and write that in what we call a completed square form, okay? Because if you can take a quadratic and write it in the completed square form, it will reveal a lot of information, first of all, about where the turning point of a quadratic is, and then hence where the axis of symmetry is, and so on. And only when I've done those two in detail will I move on to cubics, and then on to exponential functions, and then onto logarithmic functions. Okay, so all we're doing here is we're transforming. That's it. We're changing the functions that we begin with in order to represent another function or have a different shape. Now, what I want you to remember is this, that the three types of functions, the basic three, the linears, the quadratics, and the cubics, okay, they all have what I would call a fundamental starting point, i.e. x is the fundamental starting point for linear equations, okay? X squared is the fundamental starting point for a quadratic, and x cubed is the fundamental starting point for a cubic equation. And once we understand that they're the starting points, then if we add in a coefficient in front of the x, or we put a constant after the x, we can see then how they will change as those additions or as those coefficients are added in. So I'm going to start with linear functions first of all. And when one or more parts of a function change, the corresponding graph will reflect that change. And that's all we're looking at. And there's the key word, change, okay? It's a function that changes, how we change a function. For linear functions, f of x equals mx plus c is what we call the slope-intercept form, okay? Now that is perhaps the most useful form of an equation of a line. F of x equals mx plus c for two reasons. And you can see them highlighted there, one in red and one in blue. The coefficient of x, after you've rearranged your line, okay, into this form here, the coefficient of x will always be the slope of the line. And the final constant c will be where the line cuts the y-axis, okay? So just for example, say I have a line, let's say, 3x minus 8y plus 7 is equal to 0. Okay, let's just say, if I was to take that line, and we'll call it the line L, if I was to take that line and rewrite it in what we call slope-intercept form, all I have to do here is obviously isolate y, because f of x, don't forget, is another name for y. So what I'm going to do is I'm simply going to isolate y. So therefore, these two must be eliminated from that side to give you minus 8y equals, now if I eliminate these, I'm going to subtract 3x and I'm going to subtract 7. So I'm going to do the same thing on the other side, minus 3x minus 7. And the final thing then to do is to divide both sides by minus 8 to get y on its own. So minus 3 over minus 8x minus 7 over minus 8 is your final constant. Now, that is in the form y equals mx plus c, which means that the coefficient of x, 3 over 8, is my slope of that line. And then also we have minus 7 over 8, which is better known as 7 over 8, as being the number on the y-axis that this line will go through. Okay. Now just a word about the slope. The slope, as you can see here, is 3 over 8. What does that mean? That means that the rise of the slope and the run of the slope are in that particular ratio. So for every 8 units that we run along the x-axis, we will rise up 3. Or put it the other way, for every 3 units we rise on the y-axis, we will run across 8 on the x-axis in order to work out the slope. And that will help you later on when we come into trying to graph these things and see what they actually look like in terms of their coefficient of x and the constant after the x. Okay. If m changes, which is the slope, then obviously the slope will change. And what that means is that if you have an m changing, your line is simply going to change its lie in terms of the x-axis. So the way in which it lies down or stands up, that will be changing if we change the value of m. If c changes, then the point of intersection with the y-axis changes. So in other words, if you change m, you'll change how it lies, okay? But if you change c, you'll move it up and down because the numbers through which it goes on the y-axis is going to change. So let's take an example. The fundamental linear equation is y is equal to x. And what that means is every point on that line has both the same x value and the same y value. So there'll be 0.22, 4, 6, 6, -2, -2, -4, -4, -6, -6, and so on. Okay, so that's the most fundamental linear equation we have. And again, the first thing you've got to do when you're given a function is generate a table. So there's your table of values which you plot on your x, y axis. And don't forget that every time you plot an x and a y axis, you must label them as so. Every other linear equation is what I would call a deviation from this, or a derivation from this, okay? So if I can remember that y equals x is the most fundamental linear equation we have, well then, as I toy around with the x, all I've got to do is reflect the changes around x and the function on the graph itself. Watch. Here's a work example. The graph of the function y equals 3x minus 4 is shown. Now, before I do anything, let's just examine what that means. First of all, it means that it's following the format y equals mx plus c, which means immediately that 3 is equal to m and minus 4 is equal to c. Now, what does that mean? The slope is 3, and the place where it passes through the y-axis is minus 4, as you can see there. Now look at this for a nice way to put them together. If it's going to cut the y-axis at minus 4, and the slope is 3, don't forget what the slope is. The slope is the rise over the run, okay? Which means really that we can say it's 3 over 1. So what I could say here is this. If it cuts the y-axis at minus 4, then all I need is one more point in order to show me what direction this line is going to lie in. And what I could do is the following. From that point of intersection with the y-axis, I can bring in the slope. Rise up 3 units. Okay, so let's go up 3 units. That's going to bring me up to minus 1. And then let's go out 1. Let's run out 1 unit, which will bring me to there. So in other words, there's enough information in the equation itself, what we call the slope-intercept form, to actually graph the line. And that's what we've done there. So in this case, you probably wouldn't have to generate a set of points if you were able to show that you understand how the slope-intercept form will reveal where the 2 points are. Otherwise, if you're not happy with that way, stick in 3x minus 4 onto your calculator, generate a set of points, and then just draw your line. Totally up to yourself. Okay, but here's what they want me to do with it. So now that I've graphed 3x minus 4, what do they want me to do? They want me to sketch the graph, first of all, of y equals 3x plus 2. Let's just take this one first. Y equals 3x plus 2. Now take a look. Compare this graph to the original. And the first thing you'll notice is that the slopes are the same. If the slopes are the same, the lines are going to be parallel. So we expect a parallel line. The last number is the number that the line passes through on the y-axis, or where it cuts the y-axis. The original line goes through minus 4, but they're telling me now that this line will have the same slope and pass through the point plus 2, which is here. So therefore now what I expect is I expect a line to go through the point 2 totally parallel to this. So how am I going to draw that? Well, let's take a look first of all and see what happens in relation to this. It's the same slope. So how did I get from minus 4 using the slope of 3? I went up by 3 and out by 1. So the same thing applies here. You can go up by 3 to 5 and out by 1. And if you look carefully, if I join those 2 points together as best I can on this thing here, I'm going to end up getting a parallel line to the original 3x minus 4. Okay, and that line there is y equals 3x plus 2. And notice it's parallel. Now I don't have a ruler for these things. If I had, it'd be much handier. I don't have one, so apologies for that. But that's the line 3x plus 2. Same slope, different intercept. Same slope means parallel, different intercept. Locate that point and draw through it. There's the first one. Okay, the second one says that they want you to sketch the graph of y equals 3/4 x minus 4. Now this time, you'll notice that the point, let me just get rid of all the writing there, that the point of interception on the y-axis is the same. So that point there is still going to be used when I'm drawing this graph. But now the slope has changed to 3/4. And what does that mean? That means that the rise over the run is 3/4. So if I take my starting point as minus 4 on the y-axis, to get another point on the new line, I'm going to rise up 3 units. Now again, rising up 3 units brings me to here, and I'm going to run out 4 units this time, which brings me to here. So the new line is now going to look something like this. Oops a daisy. Something like that. I've missed a point completely. So let me just get rid of that and do it again if I can. Little bit better. So starting through that minus 4 and trying to aim to get through that point like that. Okay, and that point is y equals 3/4 x minus 4. Notice that it has the same starting point, minus 4 on the y-axis, but the slope is different. Now here's what I want you to recognize. If the value of the slope is less than the original, then the slope will be less obviously than the original line. The line will lie down a little bit. So you notice here, it's actually gone down by this much, the slope, okay? If the coefficient of the new line is higher than 3, then obviously we would get this line standing up, getting closer towards the y-axis. So that's what you need to look at when we're dealing with linear equations like that. They're quite straightforward. There's only 2 changes we can make. We can change the slope, which changes the lie of the line, and we can change the final constant, which is simply the point that the line will go through on the y-axis. Okay, now Desmos is a lovely way. You can always check on Desmos yourselves. I'm going to leave that on the slide. You can check it yourselves. Desmos will just allow you to go through the graphs that you're going to draw on your copy to make sure that they resemble the answers that you need. Okay, so don't be afraid to use Desmos. I'm not going to use it here just yet. I'll use it later on and show you how it works, but don't be afraid of it. That's a live link, by the way, so when you get the slides from me, you can go through Desmos yourselves. Okay, so what about quadratic functions? Now, quadratic functions, as we know, always have an x squared term, and if they have an x squared term, that means that they're going to turn once. So we're all familiar with the fact that a positive quadratic equation is u-shaped and a negative quadratic equation is n-shaped. Now, there's loads that I can do with these. Okay, first of all, I can change their width like that. I can make them narrower, or I can make them much, much wider, like this one. Or I can move them left and right, or up and down. So there are 3 types of transformations that I can do with a quadratic function. I can change the width of the arms, I can move them up and down the y-axis, and I can shift them left and right on the x-axis. So therefore, there must be 3 points of interaction on the quadratic function that will allow me to do that. So let's just take a look and see what the quadratic functions allow me to do. Okay, so there are 3 transformations, as we said already. The width, which is how close the arms are to the y-axis, if they're close or if they're far away, narrow or wide graph. Vertical shift, that's up and down the y-axis, and a horizontal shift, which is left or right around the x-axis. How do we control the width? Now, if we want to get the arms to be wider or narrower, all we have to do is change the coefficient of x squared. Now I have an example here. For example, let's say 7x squared. Okay, I've got 7x squared, I've got 5x squared, and I've got 10x squared. Now obviously x squared is your starting point. X squared means that you are most definitely quadratic. 7x squared, because the coefficient is big, the larger the coefficient, the narrower the graph. Okay? So 7x squared would be narrower than 5x squared, but at the same time, 7x squared is a little wider than 10x squared. Now, what the hell does all that mean? Watch. Let's go back to the very beginning. The most fundamental part of each of these three examples is x squared. And x squared goes this way. It goes through 0, 0 and takes off the other side. Okay, so let's just say that's y equals x squared. Now, 7x squared is going to be much narrower than that. It's going to have the same turning point, but it's going to be very, very narrow. See? Like that. So you could say that's a sketch of 7x squared. Now, 5x squared won't be as narrow. So 5x squared might be in here, like this one. Again, turns in the same place, and out this way. So that might be 5x squared. And lastly, 10x squared, having such a large coefficient, will be very, very tight to the y-axis. Something like that. So therefore, the larger the coefficient, the narrower the graph. The smaller the coefficient, the wider the graph. So if I was to take those three, I've just got rid of all the writing. If I was to take those three examples, 7x squared, 5x squared, and 10x squared, here's what I'd say. The widest one would be 5x squared. The narrowest one would be 10x squared. And the one that would be in between those two would be 7x squared. Okay, so that's how we control the width of the graph, by changing the coefficient of x squared. Secondly, we want to talk about the vertical shift, moving it up and down the y-axis. And how do we do that? Well, we do it the same way that we did it with the line. We change the value of the final constant. So therefore, the value of the final constant will always alter the position of a graph in terms of the y-axis. Okay, so if I add a constant, and please remember that constants can both be positive and negative. So you can add a positive. If you add a positive constant, it moves upwards. If you add a negative constant, it moves downwards. So vertical shift is achieved by adding a constant to the equation. So let's take an example here again of 5x squared. So let's just take the x and y axis again. Now, 5x squared, the most fundamental part of 5x squared is x squared. So because it's 5x squared, it's going to be narrower than the usual x squared. So something like this. Okay. What happens then when I have 5x plus 2? Now, the plus 2 simply takes that U shape and pushes it up 2 units. So in other words, if this turning through 0, well then what it's going to do is it's going to move up 2 units and turn this way. See? Same graph, just 2 units higher. And if I was to look at 5x minus 7, what does that mean? Well, that means, let's say minus 7 is down there, that the U-shaped graph would now turn at minus 7. So you get a situation like this. Same graph, just 7 units lower. So in order to get the vertical shift, i.e. the movement up and down the y-axis, you simply add on either a negative constant or a positive constant. And by adding on a positive constant, it shoots up. And by adding on a negative constant, it shoots downwards. Okay? And the final transition I want to look at, or transformation I want to look at, is what we call the horizontal shift around the x-axis, moving it left or right on the x-axis. To do that, you have to add a constant directly to the x. Okay, now be careful with that. So x plus 2, for example. X plus 2 would simply mean, now if you take out the x plus 2, and this is what I want you to think of. Take out the x plus 2, set it equal to 0, and solve it. Okay, what does that mean? That means, I hope everybody understands, x is equal to minus 2. So in other words, the movement on the x-axis is going to be 2 units. What way? To the left-hand side. Because minus 2 means back 2 units. So it's not the direct constant that's attached to the x that tells you how to move. It's taking out the x plus 2 expression, setting it equal to 0, solving it in order to find out how do I move this graph around the x-axis. Okay, so you take the x plus 2, you set it equal to 0, you solve it, and that then tells you that the horizontal shift will be minus 2 units, meaning back 2 units along the x-axis. So please keep in mind that we talk about the horizontal shift being achieved by adding a constant, again positive or negative, directly to the x in the x squared term. So what we mean by that is, if it's x plus 2 to b squared, then the plus 2, if you bring it up here as x plus 2 and set it equal to 0, becomes minus 2 when it's solved. So therefore the graph is going to use 2 units, or move I should say 2 units back towards the left hand side. Okay, now the final sentence there, also in this form, the constant squared is the y-intercept. Now what does that mean? Well, in this case here, we've got x plus 2 to be squared. What does that tell me? It's telling me, first of all, that x plus 2 equals 0 means x equals minus 2. So that's telling me that the graph is going to shift back 2 spaces to the left-hand side. But it's also telling me, if I take the plus 2 and square it, that this graph is going to cut the y-axis at the point 4. So again, there's plenty of information in here. The number that's directly attached to the x, now keep that in mind, it's added to the x. The constant that is added to the x term has to be taken with the x term as an expression, set it equal to 0 and solve it to work out how I'm going to move horizontally, but then that number squared will also be the number on the y-axis that the graph is going to pass through. Okay, so we really are delving into these graphs and these expressions to find out, what does the function tell me in its raw algebraic state. So let's take an example, because sometimes it's much easier to do this when you see an example being done. The fundamental quadratic equation is x squared. So no matter where you go with your functions, you're always starting with the reference of x squared. And please keep that in mind. The reference quadratic equation is x squared. It looks like this. So again, use your calculator to generate your points and plot your points. Okay, so that is what we would call your fundamental quadratic equation. Now, what can I do to x squared? I can do loads to x squared. The first thing I can do to x squared is I could put a number in front. Let's say, for example, 3. Now, what would happen if I went to 3x squared? Well, the bigger the coefficient, the narrower the graph. So you get something like this. Still turns to the same point, but it's narrower. Okay, so you could say that's a sketch of 3x squared. What would happen if I had x squared plus 2? Well, again, actually, let me just take that one there off. Take that off. Take that off. What would happen if I went to x squared plus 2? Well, in that case, we're told to begin with the fundamental x squared, there it is, but to move it up 2 spaces on the y-axis. So therefore, that point goes to there, that point goes to there, that point goes here, and so on. So you now get a graph that looks like that. And notice it's 2 units up along the y-axis. And finally, I could also just take the x squared and turn it into x minus 3 to be squared. Now let's think about that. X minus 3 to be squared. What does that do? That's going to take a horizontal shift, because the x has been directly attached to a constant value, which in this case is minus 3. So we take the x minus 3, we set it equal to 0, and we solve it. X equals 3, which is now telling me that I have to move this graph 3 spaces to the right hand side on the x-axis, which will move that point to here. It'll move that point 1, 2, 3 spaces to there, and it'll move that point 1, 2, 3 spaces to there. So the reference points on the original graph are always a great thing to have, which means now my graph is going to move horizontally to this position. Okay. And if I was asked, well, where is the new graph going to cut the y-axis? You take that value of 3 and you square it. And that means that I now know that the new graph will go on and it will cut the y-axis at the point 9. Okay, let's move on. Let's take an example. So here's an example from, and it's a worked example in your book. It's page 136127. It's question 6.8. Now it's done in your book as well, but I'd rather you follow through the logic that I'm going to present to you here. Graph the function x plus 2 to be squared. Okay, so again, if you want to use your calculator, you must generate your table of values. Okay, I'm not going to do the table of values here, but you have to do this when you're asked to graph the function. I haven't got the time to do it, so I'm going to skip that part. You can't. when you're drawing your graph, you must put your table of values in. So graph the function f of x equals x plus 2 to be squared. So you go to your calculator, okay? And just in case, actually I might just show you how to do that on the calculator. Just give me a moment now. Actually, no, I won't. I'll stay where I am. Let me see. Let me just discard that. I didn't want to do that now. I didn't want to end the show. Anyway, it doesn't matter. Let's see if I can go back, keep them, discard them. Okay, and let me show you how to use the calculator here. Here's me. Okay. Now, just in case that people aren't too sure what to do with the calculator or how to get your table of values, just in case you're not too sure, here it is. We have, first of all, our shift function, our menu, okay? And our menu, if you have this type of calculator here, I'm going to just take out. So in your calculator, I know your calculator looks something more like this one now, all right? But this one does kind of the same thing. So your menu, you look for your table, and your table is number 3. So we're going to go to number 3, and the function I want to use here is x, so it's alpha x, see that, alpha, and the little red x, so alpha bracket if you want to, minus 2 to b squared. Okay, so that's the function I want to use. Press equals. Now, what did it tell me it wanted to work with? In the domain, oh, it's x plus 2, I'll change that in a second. In the domain, minus 5 to 1. Okay, so we don't need a second function. No, thanks very much. So just press equals to carry on. Actually, what I'm going to do, I'm going to go back there. I'm going to delete that. I'm going to go back and put in a different function. Delete it altogether. Okay, so menu 1 and then menu 3. Okay, so back into your table. Now, it's x plus 2 to be squared. So bracket alpha x plus 2 to be squared. Okay, they want me to start, I don't want a second function, not just yet. So they want me to start this time at minus 5, isn't it? And go to 1. So minus 5, see? In the domain, minus 5 to 1. So minus 5 is my starting point. 1 is my finishing point. And what steps do you want to take between these? Well, normally take 1, okay? So normally take steps of 1 and press equals. And there's your table. So your table of values will be minus 5, 9, minus 4, 4, minus 3, 1, minus 2, 0, and so on. And you recreate that table on your page, okay? So that's how you use your calculator. Now, let's go back to this one here. Back into my show, if I can. And there's the graph. So when you plot your tables, that's what you're going to get. In the domain, minus 5 to 1. So what do they want me to do with it? Now sketch the graphs of these two. G of x equals x minus 1 to be squared. Now, first of all, I want you to compare x minus 1 to be squared to x plus 2 to be squared. Notice that if you take out x plus 2 out of here and set it equal to 0, what that tells you is that this graph is operating at 2 units to the left of 0. See that? There it is. So that's where this graph is operating. Meaning now that if I change the plus 2 to minus 1, let's just take that out. X minus 1 equals 0. X equals 1. So this graph, g of x, is going to operate where? It's going to operate at that point, which happens to be 3 units over. So it's now going to operate at x equals 1. Okay, so we're moving the entire graph this way, and that means all points are going to move that way. So you could, if you wanted to, take, for example, minus 3, 1 and shift that over by 3 units as well to here, just to get a kind of a reference, a feel for where they're going to be. And you could also take this point here, which is at minus 4, and move that over 3 units, 1, 2, 3, just to get a feel for what the graph is going to look like. And you notice straight away that this graph is going to be like this, see? Down here, and then go away again. So that's the graph of g of x. Okay, and then finally, part 2. It says graph x plus 2 to be squared minus 5. Now compare that to that. So in other words, the first part of this function is exactly the same as the original. The only difference now is that we're adding on a constant of -5. And you're adding on a negative constant, which means the graph is going to drop by 5 units. Okay, it's going to drop by 5 units, meaning this point here is going to drop to -5. This point here is going to drop to -4. This point here is going to drop to -4. So they're all dropping 5 units, and that's what you've got to keep in mind. So 1, 2, 3, 4, 5, and you're just going to replicate the same graph 1, 2, 3, 4, 5, but 5 units lower. So now you're looking at a graph like this. And that graph is the second one. That's x minus 2 to be squared, or x plus 2 to be squared, I should say, -5. So what did the first one do? The first one, because the value immediately after the x changed, then there's going to be horizontal shift, okay? And in the second one, because we added on a negative constant, the graph is going to drop. So we ended up in the first one getting a horizontal shift, and in the second one getting a vertical drop of 5 units. Okay. Work example page 139, question 17. Now take a look at this one. The graph of the function y equals x squared is shown. Now I've color coded this more than your book can. So that's blue, so that's the function there, y equals x squared, okay? Which is your fundamental quadratic expression. Use this graph to match the following functions with the functions that are shown below. So you're given 2 functions here, and each of these is either represented by the black function or the red function. And we've got to try and figure out which. Now the only difference between the black and the red function is their horizontal shift, meaning that the only difference between the black and the red function should be the number immediately after the x term. So if I take x plus 1 and take it outside, set it equal to 0 and solve it, that means x equals -1. And if I do the same thing here, take the x minus 5, set it equal to 0, that becomes x equals 5. Meaning what? Meaning that this particular graph has induced a horizontal shift 1 unit to the left hand side. So 1 unit to the left hand side from the original function obviously is bringing me to the red one. So that there is x plus 1 to be squared. See? And then this one is generating again a horizontal shift on the x-axis of 5 units to the right hand side. So there's my original starting point, and 5 units of a shift to the right hand side brings me to this one, and that's x minus 5 to be squared. So they're quite easy to do as long as you remember coefficients vary the width, a direct addition of a constant to x causes a horizontal shift, and then finally any other constant just added on at the end, positive or negative, causes a vertical shift. Okay, last one before I give you some to do yourselves. The graph of f of x equals x squared plus x plus 2 is shown. Now there's the graph, okay? So this is the original one here, the bottom one, the one in blue. Use this graph to match the following functions with the functions that are shown below. So you've got g of x and h of x. Now there's 2 functions above the blue one. We're not too sure yet which is the g of x and which is the h of x. So I want to see, is there enough information in here to tell me which one of these functions is g of x and which one is h of x? Well, first of all, let's take a look and see what we started with. We started with x squared plus x plus 2. Okay, notice the final constant is the number it's passing through. Do you see that? So therefore, it could be enough to say that the final constant is where these 2 graphs are going to pass through. So in other words, g of x should go through the y-axis at plus 6. Ah, there it is. So that's g of x. And h of x should go through the y-axis at plus 4. So straight away I've got enough in just a constant alone to represent each of the unknown functions by either g of x or h of x. Is there any other way to do this? Well, let's take the coefficient of the x squared term instead. Notice here that we start off with x squared. And in this one, we've got 3x squared, and this one here, we've got x squared. So we know what the blue one is, okay? But don't we also know from previous stuff we've gone through in the previous slides, that the coefficient of x squared represents the width of the graph. So if that has a coefficient of 1 and this has the same coefficient, then h of x and f of x will be the same width. See that? And you'll notice that there and that they seem to have the same width. So that has to be h of x. Now, what about g of x? G of x has a coefficient 3, which narrows the arms of the graph somewhat. And if you take a look at the one that's left up here, that's a narrower graph, meaning that if that's narrower than the original, well then this must be g of x. So there are actually plenty of ways for us to decipher what function is which, as long as we have a starting point and as long as we're given the graph of some function to compare to. Now I'm going to stop there because that's enough for me, and I'm going to ask you please to go to page 139 of your textbooks and take a look at questions 13, 14, 15 and 19. And again, take them carefully. If you're asked to graph them, use your calculator to generate the table, write down the table, plot the points carefully. And then, by means of looking at the coefficient, or by looking at the final constant, see if we're doing a narrowing of the graph, a widening of the graph, or a vertical shift up and down. And with the quadratic functions, if the x term has directly a constant added to it, as in x minus 4 to be squared, or x plus 3 to be squared, or something like that, that's going to represent the horizontal shift. Okay, so the coefficient is the width, the last constant is the vertical movement, and any constants then that are attached directly to the x squared term, they are the horizontal movement of that graph. So I'm going to leave you with those, and we'll come back tomorrow with a lesson on how to complete the square. And when we get the completion of the squares done, then we will be able to take from that more information about the graphs that we're dealing with.